So I assume that you are here, guys, because you are looking for ideas about resistors or resistance, which are essential concepts in the physics chapter under current electricity. Here are the competencies that you need to understand about resistance, these highlighted ones here. If you're not familiar with the word resistor yet, here you can think of it as something connected as a component of a circuit, like that, with the EMF provided by source here. This something has subatomic particles like neutrons. Examples are these ones in these materials, with some protons too, these ones, and electrons. I'll just draw one electron, but naturally materials have equal numbers of protons and electrons unless they are charged. Technically, all things have these particles and therefore may be called a resistor when connected as part of a circuit. In our diagram, these electrons, when moved by the electromotive force by a source, will encounter obstacles due to the other things inside the materials, which, as a result, provides a resistance or opposes the flow of charges, in this case, the moving electrons. This resistance is a new physical quantity for you, which is possessed by any resistor, a measure of how large or small its opposition to flow of charges, or better say, the current. Since the way subatomic particles may be arranged differently from one material to another, we have different types of resistors. Two of the most common ones are here: fixed resistors and variable resistors, which you might have already seen in your science labs. The symbol for the fixed resistor is this, and for the variable resistor, it is somewhat similar to that, but with this arrow to signify that the value of resistance can be manipulated. Now, let us use those to create a circuit where we could determine a resistance value based on its operational definition. Here we have a circuit with a fixed resistor with, say, resistance R, and the other components is also a resistor. Since it may have different value as compared to the first, we can give a symbol to differentiate the two. A hyphen like that can be used. It will really be different as we are going to use a variable resistor here. See, that's a symbol we had a while ago. And of course, an EMF here in our source. So we already defined resistance as opposition to current. Operationally, resistance of a circuit component is the ratio of the potential difference across that component, or the voltage to the current that passes through that same component. In symbols, resistance R is equal to V divided by I. If you want to know the resistance of a component, measure the potential difference or voltage across the component. We use voltmeter here to do that. And for the current, we use ammeter to measure it. We have to place it in series like that. Now, the purpose of the variable resistance is to allow us to manipulate current, and so we could measure the corresponding voltage across the resistor. Let us have a ready graph here with the voltage slash volts along y-axis for the dependent variable and current slash ampere along the x-axis for the independent variable. Let's say after a couple of hours we did several attempts by varying the resistance of the variable resistor so we could get different values for voltage V, which is dependent on the values of current I from this ammeter here. We then plot the values like the obvious result of zero current corresponding to zero voltage here, then followed by this pair of values, then this pair, and so on. So we could get something like this. With this kind of distribution, I assume that you already know that we should use best fit line here. A graph like that which best fit our experimental data. Say, imagine we got this from a lab experiment. And from this graph, we could deduce the relationship that voltage is proportional to current. At higher current, voltage is greater. Lower current is going to be lower voltage. This relationship is called Ohm's law, another important law in the study of electricity. As for the operational definition, we can take the gradient here, and that gradient is voltage divided by current. The gradient, therefore, whatever we get, is the resistance of this component. If a material follows this relationship here, V varies directly with I, which is the statement of the Ohm's law. The material is said to be ohmic material. The graph of this kind of experiment done for materials like this is always a straight line. If it curves like this or this, we say that the material is non-ohmic material. Since we have current here, we can just say ohmic conductor or non-ohmic conductor instead of using this broader term material. Anyway, current is present and therefore these materials must be conductors. Okay, so that's basically all about it. To summarize, let's look back at this equation which comes from the operational definition of resistance and also can be taken from the Ohm's law. The statement that voltage across a component is directly proportional to the current that passes through it, with the gradient of a graph from which this idea came from is the resistance. For the unit of resistance, it has to be volt per ampere, where volt is a unit of voltage in the formula and ampere is a unit of current in the formula too. In the SI system, this 1 volt per ampere is defined to be 1 ohm, the SI unit of resistance, named after the person behind the Ohm's law. Apart from this R equals V divided by I formula, you will encounter another equation that can quantify the resistance of a conductor. If you're interested in exploring the idea, it is here. Resistance is equal to a material dependent constant, this resistivity with the symbol ρ, and length L divided by area A. I'll talk more about that in our next session. Alright guys, bye.